So let's see. This one, it covers a lot of chapters, but most of the chapters have like 2 or 3 sections. So it's chapter 4, 5, 6, and 7. Long. So 4 was the x, p of x stuff, the binomial stuff. Please, heater, stop. Let's see. It's gonna work today. There you go. This stuff. And then it was this kind of stuff. Coolness. What kind of distribution uses this kind of stuff? Got P and Q. Binomial. It's got 2 probabilities. That's the binomial. Do not use these formulas when I give you a table of x's and p of x's. I still have people trying to use these when I give you this. No, it's not going to work. It's like using a hammer to turn a screw. That's not going to work too well. Well, I don't know. You can maybe make it work. That's chapter 4. Chapter 5 was the uniform stuff, and really just continuous distributions in general. No formulas. There was a problem in the homework and on the practice test. Let me see if you guys can take what I'm about to say, that dealt with the mean and the standard deviation of the uniform distribution. There's a formula that's got divided by 12 in it. And some semesters I have students that are like, why is it 12? And then I actually bring a printed out copy of the proof of that formula, and they're like, oh, okay. So it deals with some calculus stuff. That's why the 12 is in there. The mean and the standard deviation of a uniform distribution is not something that comes up a lot. So I am not going to ask a question about it on the test. There you go. Why was in the homework? Just so you know it exists. What did I promise you? Every time we have a new distribution, a new way to have data, there's got to be another way to do the mean and another way to do the standard deviation for that situation. So I just want you to realize those exist. But it's not that important. I'm not going to ask you about it. You guys with me? So don't even put them on your formula sheet. So you guys remember there's a formula square root of b minus a squared divided by 12? That's the standard deviation of the uniform distribution. Yeah. That's fine. It exists. That's all I want you to know about it. Okay, maybe. So chapter 5, there's nothing to write up here. You have to know how to set up a uniform curve. You have to know how to calculate probabilities. Okay, big old rectangle. Wow. Chapter 6, of course, brings back this formula. It brings back this idea here. Those came up in chapter 2, but now we make it a little more formal. That's chapter 6, to be honest. Right? The other stuff is using the chart, drawing the pictures, all this kind of stuff that doesn't belong on a formula sheet. Be really careful, by the way, if you have written notes on your z-score chart, you want to come see me and get a fresh copy of it, because I will be collecting them. And if you have notes on your z-score chart, you're going to lose points for it. That's kind of silly. Okay, how about that? And then chapter 7, which is what I want to kind of focus on right after we finish this. I want to do a few examples of chapter 7. Chapter 7 introduces this idea. That's where if I take a sample, the sample mean should make a skinnier distribution. The spread should get smaller. Okay. So if you want to, here's my claim about this. This formula never changes. If you don't think I'm crazy already, at the end of the semester you definitely will, because you'll say, look at all the different z-scores formula, Jeff. But they're always, the z-score is always my data point minus the middle divided by the spread. That's what it always is. So if you want to, right here you can put z is x bar minus the mean of all the x bars divided by the standard deviation of all the x bars. It's the same stupid formula, right? We're going to do a few examples of that kind of problem right away. So I wouldn't even write this down if I were you, but you can if you want to. Any other formulas that you think should be up on your formula sheet? Anything you think I missed?
Just to be clear, chapter 3 is not on it.
No. Chapter 3 had its own thing, its own day in the sun. It's going to come back on the final, though. Be careful. But this one, I figured 4 chapters is enough for a test. Yes? There's a what now, sir? Yeah? So the uniform one, right? Yeah, I told you. There's a problem in the homework like that. There's a problem in the practice test. But it's not going to be the test. So why? So let's talk about why I did that. Why do I have to be so extra evil, Jeff? Math is already hard. What's wrong with you? Let's do this first. I want to explain number 6, but I want to do a few examples of this, and then I'll come back and explain why I put number 6 on there. Okay? So everybody got, I'll let you guys finish copying that down. I want to, let's see. I do have a handout. I don't want to give it out yet. Did I bring it with me? Yes. I love that my office is so close. I wish that could always be true. But I brought them with me. Yay. All right. How we doing? Everybody got those? Where are you at? Okay. Cool. I'll leave these up here for a minute. I'm not going to redo the whole lecture. We talked about why it makes sense that the standard deviation gets smaller, but we haven't done a lot of concrete examples of the kind of problem. So here we go. Just to remind you, the central limit theorem. And real quick, why is it called that? If I have a population with a certain average, so right now the population of gross month students has a certain average shoe size. Are you with me? Right? So that's a number. That's whatever that number is. There's an average shoe size of all gross month students. If I take a sample of gross month students, a random sample, that average should be how related to the overall average. If I take a random sample of 100 gross month students, would I expect their average shoe size to be very different from the actual average shoe size? No, especially if it's 100 randomly selected. Okay, you with me? A little bit? Okay, at least physically. So if I take 1,000 gross month students, then their average should even more be closer to the mean. So what central limit theorem means, in the limit that my sample size gets really freaking large, it's going to tend to be towards the center. It's going to tend to be closer and closer to the middle, the center. And that's where the name central limit theorem comes from. And that's something we knew on day 1. We knew the bigger the sample we take, the closer it should get to what the real information is for the whole population. You knew that when you came in to this class. Okay. You guys are beat up, I'm sorry. What does this say? It says three things. It says the mean of the sample mean stays the same. So another example. There's an average age right now in here. I could take each person individually and calculate the average age. Would that number change if I took two people at a time? I think we talked about this last time. And I made the silly remark about if I just start taking two people, you don't all of a sudden everybody become older or younger. Right? I'm taking two people, turning into a baby, oh shit. Okay, so it's not going to happen. It's going to be the same average. So if I take groups of size n, and I do all the sample averages of groups of size whatever, the average of those has to be the actual average. I can't suddenly change what the average is just because I'm taking groups. The second thing is that it says the standard deviation of the sample means. So remember the Florida thing? When I regraphed it for groups, the standard deviation got smaller. And like we just said a minute ago, if I take a larger and larger sample, my spread should get smaller and smaller. There should be less and less samples really far away from the actual average. That's exactly what this formula says. As n gets bigger, the new spread gets smaller because I'm dividing by square root of n. And then finally, the last thing, I want to make sure that you guys get this. Did I say this last time? If n is greater than 30, then the result becomes normal enough, approximately normal, or what I call normal enough. In order to understand an idea, you've got to kind of go with me as I explain it. So we've talked about this idea a lot, but as I pick more and more samples, more and more of them should be close to the actual average, which does sound to be becoming much more normal. And we did that example of the picking numbers out of a hat. And because that started off so nice already, I only had to take samples of 2, and it already looked more normal on that sheet that I gave out. So this greater than 30 is really just in case the beginning distribution is disgusting. It's going to take more than 30 to kind of smooth that bad boy out. Bye-bye. All right. So here's an example. Let's see, given the mean is 38, the standard deviation is 2.9. Take a sample of 42. What's the probability that the sample mean is more than 39? Yeah, I know. That thing needs to stop. Oh well, I don't have any control over it, I don't think. Lockdown, shit. All right. I don't know if any of you guys have classrooms in the 50s, 51, 52, 53. The AC's out. Today's gonna be great. So this morning, it's like, let me give you some heat just to get you going, whatever. All right. Can anyone identify, there's a problem with this question. What do I want to use eventually to get the answer to this? The z-score chart, right? What has to be true for me to be able to use this? More than that. Has to be normal distribution. I can calculate a z-score all frickin' day long. I can throw x and mu and sigma in there, but what's the only time I can use this to make it into a percentage if it's normal? Do I say up here that it's normally distributed? No. But why can I still do this problem? I love it. That's not good enough, little Miss Lawyer. You guys with me? I didn't say it was normal, so you can't assume it is, but what is it about this that tells me it is, based on what I just said?
It's not greater than 30. Oh, it's close to 30.
What's n?
42.
N is 42, which is bigger than 30, so the central limit theorem says go ahead. So if I don't say it's normal, what will save your ass is if the sample size is big enough to make it smooth out and become normal. And again, I mean, if you want to understand, you should go back and watch that lecture about Florida and when we took groups and what should happen. And then what did we do? We actually did an example with actual numbers, not just made up Florida ages, and we saw it happen. Right? We did. We actually did that together. So how do I proceed? So here's how I proceed. So I know I can do something. How do I draw this picture? What goes in the middle? 30. 38, because that's the mean. And I'm interested in 39, and I want the area above. So here's how this guy works. Right. So this right here, this number right here, that is the spread of individuals. So if I had a question about an individual, that number makes sense. I can use that number. Is my question about an individual? No. What's my question about? A group of 42 things, right? You really want this, you gotta go with me here. This is almost too nice to believe. So this number by itself is the spread of individual data points. I have a question about a group of 42. So I can't use this. I have to create the spread for a group of 42. How do I do that? So how do you know? This is the thing with math. You guys know this. You guys know this. All right, Jeff, I know how to do this. I just don't know when the hell to do this, right? Every math course I teach, that's one of the main issues. When do I do this shit, Jeff? When do you do this? You do it when we take a sample. It's got an N in it. You take a sample, and I ask you about the sample mean. Why does that make sense? This is for individuals. If my question is for a group, I can't use this shit. I've got to figure out what it is for groups. That's what this does. So just throw stuff in there, figure out what the new spread is. And again, remember, when I went to Florida and I took a group of whatever, didn't I get a mixture most often? Didn't the standard deviation get smaller? That formula tells me exactly how much smaller it gets. So I just throw stuff in there. What goes up here? 2.9. What's n? 42. If you put a decimal in here, please understand that makes no sense. N has got to be a whole number of things or people, right? Okay. And then, whatever the hell that is. It's like 0.5, it's around 0.5.
0.447.
447? Okay. Now here's the beautiful thing about this. It took me forever to explain that concept. How does it change an actual problem? Not by much. What do I do next to figure out this area? I want to take 39 and make it into a z-score. The only difference now between this problem and the problem from chapter 6 is this one step. When I go to make a z-score, it's going to be my data point minus the mean divided by what? The new standard deviation, yeah. I don't use that one. I use that one. I really want you to understand. The chapter 6 problems, chapter 7 adds one little step, change the standard deviation. I love you guys so much. You have to think about this. So the beautiful thing about this equation is it tells you when to use it. Take a sample, ask about the means. That's when you use this equation. Yes?
The little X with the thing over it is a sample mean.
Beautiful. So look what does this mean then? It's the standard deviation of the sample means. That's all it means, yeah. This isn't sigma divided by x or some craziness. Real quick word about subscripts. Are you guys cool with subscripts? Where's like another place you use subscripts? Does anybody remember the slope? The slope between 2 points? M equals what over what? Y2 minus Y1. So this is one of the most basic places you guys see subscripts. Subscripts. What the shit does that mean? It means a specific Y value. Y from the second point minus Y from the first point. All a subscript is it means a specific this. So what does this mean? It means the standard deviation for sample means, specifically. So that's all a subscript is it makes it more specific. Not just Y, any Y, but Y from the second point. Okay, maybe. So then how do I keep going? What do you guys get when you do this? It's going to be like 2 point something. 2.24. And now nothing changes now. The rest of this, once you change the standard deviation, the rest of it is exactly the same as the normal z-score problem. Look up 2.24. That won't be the answer. I'll have to do 1 minus. So you look up 2.24, I get 0.9875. So this side will be 0.0125. So let's do this. If you don't want to do this, you're fine. If you want to do this, I'll do this with you. Just a little extra practice on chapter 7. So try to do number 1, and I will tell you this. Look at 1A. How many people am I dealing with in 1A? So I'm not taking a sample, right? I'm doing the probability of an individual person. Why am I allowed to do that? What has to be true so I can use the sheet of answers? Has to be normal, and of course I just say it is, right? So 1A is chapter 6. 1A is old news. 1B is where I take a sample. Okay, so try to do those two. 1A is old news. 1B is going to be like that.